always start with a little Dutch.
That's right. Okay.
But we will switch to English now. I see that a lot of people already have attended, and I see more people coming in, but I say let's start because it's time. I would like to welcome everyone to this Energy Talks and Drinks Christmas Special. Very nice that you called in so close to Christmas and so close to holiday. This will be about the unlocked opportunities for the Dutch manufacturing market on floating wind. It's a second in a row due to the success of the previous floating solar Energy Talks and Drinks. We thought there's also a lot of potential in floating wind energy. So therefore, the Buccaneer Delft and Maritime Delta together with TKI Wind organized this session. And the Buccaneer Delft is an accelerator in the maritime and offshore energy sector. They create visibility for technical start and scale-ups, and they offer these companies growth support. So they connect the industry, government, research, and education. We work very well together. We already organized the previous session, and we also work on other teams together. And I say Maritime Delta. This is a partnership between companies, educational and knowledge institutes, sector organizations, and governments. And we improve the maritime cluster of the province of South Holland. And together, we want to strengthen the maritime cluster, and we focus on innovation themes like energy transition, digitalization, and human capital. And I would like to give the word to Bob Meijer. He's the director of TKI Innovation Program on Wind Energy, and he will be our host for tonight and also our moderator. So, Bob.
Yeah, thank you very much, Tessa, for the introduction. I'll start sharing my screen now. So you should be looking at a picture of a floating offshore wind turbine. I'll say a couple of introductory words also from the TKI Offshore Wind Innovation Program. And then we'll start off with our first guest. We've got a full program, by the way. Our first guest, Sarah Marshall from Atkins. And she'll tell us more about the global outlook and the challenges also for floating offshore wind. But as I said, just a couple of introduction words from my side. So the TKI Offshore Wind Innovation Program now roughly has a total research value of 350 million euros over 300 projects that are operational. And this program is executed by many companies and knowledge institutes and universities together, sometimes in the form of joint industry projects, but sometimes also real product development. And the program targets the energy transition. And what we see is that there is a massive scale-up required for our energy transition in offshore wind. What we also see is that this will not happen automatically. So we still see quite a few challenges ahead of us on this route from 2020 to 2050, where we are fully decarbonized in our energy system. And some of the challenges are related, for example, to cost. I must say still cost. We've seen a very steep decline in offshore wind cost, of course, over the last years, but it's not enough. It's definitely not enough. That is, by the way, both true for bottom-fixed offshore wind and for floating offshore wind. And of course, they have a different starting point at this point in time. But of course, we also hope that floating wind will catch up and achieve, say, the same cost reduction results as we've seen for bottom fixed. Other areas of challenges that we see is still the integration of large amounts of electric power in our energy system. At least for the Dutch part, we foresee that it will not be feasible to transport all these electrons on cables to shore. So we are anticipating also offshore conversion to other energy carriers like hydrogen, for example. And I think that may also be relevant for floating offshore wind, since these sites are also many times further away from shore, and a direct conversion to other carriers could be very interesting. And a third area is, of course, space. And space is limited, both from an ecological viewpoint, but also just from, I say, a usage viewpoint. So these three areas are the core of our innovation program. And for all these three topics, we have, say, a separate innovation themes or subjects that we address. And for tonight, this, say, the balance of plant, as we call it, is the relevant topic. And for the Dutch energy transition, bottom fixed is a likely solution. It's available and cheap at the moment. But we also see for the longer term that new foundation concepts, including floating, also for shallower waters, could be a very interesting solution. It can also reduce, for example, the cost of installation, potentially also maintenance cost. So for the longer term, we see the perspective also of floating offshore wind in the North Sea. But of course, these are very shallow waters. Now, floating offshore wind is, of course, a much bigger subject than the Dutch energy transition. And what is it? 2 weeks ago, the European Commission launched their EU offshore renewable energy strategy, which includes 300 gigawatt target for 2050 in offshore wind. But explicitly, floating offshore wind is mentioned as a key technology for areas like the Atlantic, the Mediterranean, but also the Black Sea. And I think we're very much encouraged by these statements from the European Commission that we are working towards these kind of targets. So a mix of bottom fixed and floating offshore wind in the long run. But there's still a couple of steps to be set in that area before we come to a full scale up of floating offshore wind. And also part of that publication from the European Commission, this is the current situation. On the right-hand side, you see offshore wind, roughly 12 gigawatts of installed capacity at this moment, and 40 megawatts of floating offshore wind. But it is in the most promising stages of all the other technologies that also are on the roadmap for our energy transition. And the last session for the Energy Talks and Drinks, we had about floating PV. So that is really starting to say in the lower TRL levels. But floating offshore wind, yeah, we have already projects operational right now. So we're way ahead there. So what I'd like to do now is to introduce to you Sarah Marshall, who's a principal engineer at Atkins, a well-known engineering company, and she'll say a few things about the challenges also for global offshore wind developments. Well, I'll stop sharing my screen and I'd like to hand over to Sarah.
Hello, everyone, and thank you for the introduction, Bob, and the kind words. Yeah, so I don't have any presentation slides for you. I just wanted to talk to you about the general opportunities and challenges associated with floating offshore wind. So a bit of background, I guess, just about me. So I guess to say my background is in installation and transportation of these structures, and I've been working with floating offshore wind projects for the last 5 years and fixed offshore projects in the wind industry many years before that. And I'm really seeing the different challenges that we're getting between the different industries. And one of the things that I'm focusing on is actually changing the way we look at the design of the structures, because it's being driven much more by the installation criteria. So Bob mentioned earlier about the applications in shallower waters, but going further out with greater energy yield in deeper waters. That's absolutely where we want to be going for the floating offshore wind capacity. But I also see there's a massive application in shallower water places, mainly because if you've got really challenging geological seabed conditions, you can actually sort of install a floating offshore wind farm at a much reduced cost to a fixed structure. So there's challenges sorry, there's opportunities for that. There's also opportunities for cost reduction in minimizing that time for the installation actually to be performed. So it's actually quicker to, for example, install or pre-lay anchor moorings than it is, and then hooking those up when you after you tow something to site. But we're also seeing differences in the way that we're assembling things on the quayside and those sort of fabrication methodologies. Traditionally, we've gone through lots of processes that have relied on welding methodologies, and we're seeing that it's actually changing the way we're looking at the assembly, and we're actually going more to kind of like bolted and connections, mainly because it reduces the time associated with those assembly fabrication techniques, if you like. So we're really seeing that the driving of the floating offshore wind into deeper waters is actually almost driving the supply chain to be able to respond and come up with different solutions and different methodologies for those assembly, if you like. So it's really, we're finding we're talking to quaysides, ports and harbours, and actually talking to them about their infrastructure on the quaysides and actually what methodology they're going to be using to do the assembly and supporting those installations. Because also with the advantage of floating offshore wind, you don't necessarily have to service it when it's on site after it's been installed. If you want to bring it back to port to do any of those key servicing techniques, you can then tow it back to port if you're doing any major component replacement. So we're really looking at a completely different structure, if you like, to the actual operations and maintenance of those wind farms. So it is really changing the way we're looking, and we're finding better ways to get cost reduction into it by minimizing time for installation, making it quicker to assemble and install, and also looking at that longer term O&M cost. So there are just some key highlights from me.
Yeah. So you mentioned a couple of things there also related to cost. How do you see the cost reductions? Do you see them approaching the same levels as for bottom fixed offshore wind?
Yeah, so I guess yes and no is the short answer. So I absolutely think that the learning rate and the cost reduction associated with a maturing technology you'll vastly see an improvement in those levelized costs of energies coming down with the floating offshore wind, absolutely. And especially when we reach that commercial scale, when we're starting seeing multiple offshore developments. There is obviously a challenge associated with the increased mooring costs that you don't have with the fixed bottom structures. But I believe with engagement with supply chain and trying to understand those ability to develop long lead items, I think we can see those cost reductions coming in, and I think we're going to find smarter ways to effectively moor and also combine moorings and things, and I think that's where the savings will be had. Because I think a lot of, sorry, just one slight more point. So a lot of the mooring codes and standards are actually associated with the oil and gas industry, and they come in huge amounts of safety factors, which it is incredibly important to adhere to. But we need some floating offshore wind specific codes and standards to actually address the specific codes, and I think we'll see cost reductions associated when they come out as well. Sorry.
Yeah. Yeah, these codes, I think it's an interesting topic because you would also require further standardization, obviously, in this area. If, say, the fabrication of a one-off floater is one thing, it's almost like building a new vessel. But producing like 20 or 40 of these in kind of serial production requires something else.
Absolutely, yeah, and we need the codes and standards to sort of catch up with us and to help that optimization. So you're absolutely right, they need to follow, but I think we will see cost reductions as part of that sort of standardization moving forward as well.
Yeah, I think from an engineering perspective in bottom fixed offshore wind, and I've been doing some work in that myself over the last 15 years. We always looked at very separated components and interfaces. So you got the foundation and transition piece and the turbine, the tower and then the cell and all these various components. And say integral design was always a difficult topic. Well, we got away with it by exchanging load cases on interfaces, etc. But it was never really optimal. I think for floating wind, it has to be different. So you can't separate these items anymore. What is should this should there be one integral design for turbine and floater?
So I can give you my personal opinion. I completely agree. yes, we've approached it in the past in terms of very kind of almost siloed packages that we can then exchange interfaces with. In order to achieve the sorts of cost reductions that we're going to need to make this commercially successful, we need to have a much more integrated approach, especially considering the dynamic behavior of a floating offshore platform. The design is, in terms of like the turbine and the substructure and the moorings, it's one system, and you have to consider it as one system, because each component of that system affects the other one. So the moorings take can really change the behavior of the platform itself and the turbine, and we need to have a much more integrated approach to that and that holistic perspective of it. Absolutely. Yeah, sorry, that was me kind of assuming that yes, that's what we're going to get. So yeah, so
well, this is kind of like a view that you have on these developments, but
oh, sorry, I've lost you, Bob. I don't know.
Yeah, I saw that the host muted me, so I'm not sure what that means. But my question was more like, this is your view on, say, this integral design approach, but is it already happening, or do we still see like a design of a floater and we put a wind turbine on top of that?
So I do see it happening. We are seeing developers talking to us specifically about performing that integrated role, as a sort of plug for the company. We are doing that. I think that more is required. I've also worked on fixed projects where it is very much kind of, this is our black box, this is your black box, let's interface. I think in order to achieve the cost savings that we want on a project and to develop the technology and mature it, I think we need to be more open as an industry and across industry to work collaboratively together. So
I'll have a look at the chat to see if we can pick up questions from the audience for you.
Nothing too difficult.
There's a question there is a question directed to me, but I'll pick that up later. It has to do with innovation funding in the Netherlands, so I'll pick that up later. From Ajit, is there any limitations to the size of the floating wind plants?
So is there limitations to the size of the floating wind? I didn't catch the last word.
Plans.
Plans.
So I think the full project size, I presume.
Yeah. So so there are limitations in terms of material capability. I mean, you have to take those sorts of things into consideration. Obviously, the deeper water you get into, the larger the mooring has to take into consideration. But this is not new technology in that respect. The depths and the levels of the moorings that we're talking about have already been established in sort of like legacy oil and gas industry. So I actually just think we can make improvements on it. So I don't see that as a limitation. I don't think the limitations are on the size of the vessels or the turbines themselves. I don't think we've reached the limit yet. No, I think we'll see growth. I think the limitations will be in terms of the ability to fabricate support and actually deploy in a field development. I do see there being development in the concerns for the spaces required in between the turbines themselves, because unlike well, if you're talking with fixed jacket moorings or monopiles, you have a set spacing and the standards for where you put them in terms of optimization of energy yield generation. Those still apply, but then you've got the complex issues of different moorings and how they interact and all the dynamic cables associated with it. So I think there may be lots more learning that can be done of how to either share the moorings or to develop a system for safe access to these dynamic cables and the moorings, because you're going to have to go in and monitor them, and you're going to have to be able to inspect, detach, reconnect if associated with it. So I think that those will limit the technology rather than the technology itself, if that makes sense.
But also I think for an individual floater turbine combination, you don't see any, say, limitations also in size. So the next generation wind turbines could fit with it. Is that correct?
So, sorry, I don't know if it's my internet connection, but I don't see any limitations on the sizes yet. But I'm
very clear.
Sorry.
Okay, now that was one of the questions. Another question. There are different designs for floating winds. Which design will be the most successful?
I'm assuming they mean the substructure designs. Again, my personal opinion is that there's not a design that's the most successful. It's what design is most appropriate for the location. So different substructures behave better in certain conditions, and there are places in the world which have much worse conditions than others. So I think my personal opinion is that we should choose a substructure that's most suitable for that location. But in doing so, we talked about this holistic design that considers the turbine, the substructure, and the moorings. We also have to think about where it's going to be fabricated and installed. Now, is the most appropriate solution to have a semi-submersible or a barge type structure or a spar type structure? If it can be manufactured more closely to site, that might be the most suitable solution if it is a technological suitable solution for those metocean conditions. So again, I really don't believe it's about one solution being correct. I don't think you can say it will be a semi-sub everywhere. I think it will be, this is the right substructure for this location that meets these metocean criteria and also is the most suitable to fabricate in that location.
Yeah. Okay, so that we'll still see some variation in designs. Yeah. There's a question from Koen. Will they ever be fabricated at similar cost as fixed wind? We already touched on that briefly.
Yeah.
Yes, we see the cost of floating approaching bottom fixed in the end. Yeah, is there also a probability that it will undercut the prices of bottom fixed, do you think?
I'll say we'll match it. I'm not sure we'll undercut it. I don't know. I'd be lying if I said I had confidence
for
in those
some
numbers.
designs, if you look pure at, let's say, material use, like for tension leg type platforms, the material use is quite low. So potentially it could
possible.
be even cheap.
Yeah, it absolutely could be. Yeah.
Okay. Well, in the introduction, I also mentioned what's happening now in Europe, but of course it's a global development. We see markets also like in Asia where there's say demand or potential developments. Which is going to be the first market in your view that's really going to take off? Is it going to be in Europe, or is it Asia, or maybe even the US?
I mean, you're absolutely right. There's so much excitement across the globe. So we've got developments going on in European waters, and we've got going off US waters, and we've got Japan and Korea and what is Taiwan, and also sort of closer to home. So obviously there's projects coming off the Scottish coast, but we've got in Spain and Portugal and Norway. So we've already got demonstration projects going on in terms of the floating offshore wind arrays that are already in. So that's really exciting. We've also got the recent announcements in terms, this year in terms of the ScotWind leasing arrangements, and pretty much the majority of them are in such deep water applications that they are not suitable for fixed wind structures. So it's really going to accelerate that need for floating offshore wind capability. But it's not just a European issue. The market is accelerating very quickly in the East, very, very quickly. And there is a lot of, there's a lot of excitement and a lot of learning that they've taken from the good work that we've done in the European waters. And they're basically saying, well, that's fantastic. Yes, we see where you're going with that. Let's do that then. And it's almost like we've accelerated their learning as well, potential, which I think is brilliant.
Yeah.
So I think it will be it won't be just in Europe, no.
No, but it is what I see happening also in Europe. If you look at, say, the forthcoming tenders, ScotLease, for example, but also 1st of January, the tender in Norway opens up. Of course, there are the French projects. So things are really starting to happen now. It's going to be real offshore wind farms, floating offshore wind farms.
Yes, absolutely.
So I think Europe has still got a leading position. Of course, it's very important to maintain that. And
no, it's fantastic. And I was saying to somebody the other day, I was saying, sort of 5 years ago, I was trying to convince people that it was possible to have a floating offshore wind turbine, and now and people are asking me, well, is it possible next year? Is it, how can we do it quicker? And it's like it's a different conversation. The acceleration of the floating offshore wind potential in the last 5 years has been astronomical. It's been fantastic.
Some people may even say we're not too late to jump into this market, but there are many opportunities. And I think this event is also organized around, startup companies. And I think there's a very interesting new market that you can still step into. A lot of opportunities there.
Absolutely. I guess there's some key things that maybe I mentioned or people didn't pick up on, or but I think there's huge amounts of opportunities for innovation in technology with regards to I mentioned before about the actual operational life of these, floating offshore wind platforms. They're not going to be attended by people on a permanent basis. So how are we going to get people onto them, or are we going to remotely inspect them? Are we going to be using drones in terms of robotics? We've already seen a lot of movement in that field already, but I think there's a lot of innovation that can be handled not just with the actual inspection, but with the interpretation of that data and how you can do that long-term performance monitoring. And I think we're going to get cost efficiencies through that knowledge as well. In terms of subsea inspection, we need a lot of innovation around that. It's obviously something that we're, very good at as an industry in terms of using ROVs and AUVs. But do you want to navigate one of those on an umbilical in and around a network of dynamic cables and moorings? And so, there's lots of challenges that we need problems. We need to solve those problems, and I think there's lots of opportunities for innovation there.
Yeah. Well, I want to thank you very much, Sarah, for contributing to this event with all your knowledge and experience and answering all those questions. There will be more questions. If you can around for some time, that would be great. If you can't, okay, then again, thanks again for being here. One of the questions that is still on the list is how do you position the Dutch maritime industry with floating wind? And I think we've got a couple of very good speakers also lined up who can pick up on that question. So thank you, Sarah.
Thank you very much for having me. I'll stick around. Thank you.
Okay, great. Then I would like to introduce Ilyas Bayati, who's a project manager at Marin, who's actually been working on testing all these floaters. So Ilmas, can you introduce yourself?
Yeah, sure. Thanks, Bob, for your introduction. Yeah, that's correct. My name is Ilmas Bayati. I'm a project manager in the offshore department at Marin Renewable Energy team. And I'm gonna share my screen that I have a few slides that I prepared for you. So please tell me if you can see them. Is that okay?
It's starting to show, so yes. Okay,
great. So yeah, I'm gonna talk about floating wind turbines. So it's I want to pick up a couple of tag words that I think are quite interesting from the previous discussion. One is integration. You've talked about integration and integrating the designs, and actually this brings about the fact that we also need to test in a model scale, as we do at Marin, in an integrated manner. So wind and wave simultaneously, which is not that straightforward if you think how the wave basin like Marin has been, let's say, designed decades ago. And the other point is, which is the very final and most, let's say, performant design. Well, I'm glad that there's not anyone as considered like the best one, because this means that we are able to keep working on that and keep testing the different concepts. So just I'm gonna give you a very high level talk about floating wind turbines. So as we said already, so we are going far from the coast to get high quality, high availability, and quite some space to be installing our wind turbines, which also allows us to have less social impact, which is a big topic for wind energy, onshore wind energy specifically. So we are going floating because as far as we go off of the shore, sometimes it's not, let's say, if you think about the Mediterranean Sea, it's not like the North Sea. So we have quite deep waters, and bottom fixed solutions are not applicable anymore. But the point is that we combine wind and waves. So in terms of design and expertise, we can actually exploit tremendously on the two different worlds and the expertises we have behind. But again, we have to do it smartly and in an integrated manner. So what is the point? I don't want to be too much technical, but basically, let's say if we think of a section of a blade, actually we are generating some lift and drag forces, which are based on the composition of the incoming wing speed and the rotational speed of the blade. This is, let's say, summing up along the blade, and we have the a torque, which is actually useful for the generation of the power, and a thrust. But this thrust in the overall dynamics is needs to be taken into account, because it's really adding another character to the game. So wind turbines are not floating offshore wind turbines are not like oil and gas platforms that are merely excited by waves, but we have to consider the dynamic, let's say, contribution of wind. And we can do that by developing and validating new codes, new numerical codes that need to be including a lot of different and new challenges from an engineering and also an IT perspective. But these codes are basically the tools that the industry, the offshore wind industry, needs to use to base their design upon. But these codes needs to be validated. And how this can be validated in facilities like Marine, which is at the top, let's say, rank of facilities and institutes like this. We have big facilities, big wave makers, and big, let's say, basin where we actually can reproduce the wind, but specifically wave conditions, and we can actually test scale model. So if you can see from this picture, basically what you have is a very tiny scale model, 1 to 50. This is the scale that is generally related to floating wind turbines in a very huge facility. I'm let's say stressing this concept of the let's say dimension of the facility, because this comes to be really important when we actually put also in this facility wind, in order to have let's say less blockage effect as possible, less let's say dependency on the geometry that is surrounding let's say the wind turbine model, as low as possible. Actually we need to very big spaces, and at Marine, fortunately, we are in a very good position compared to other facilities to be able to actually create these conditions. Just to give you an example, here is a picture related to the installation and the wind calibration, because what we need to do beforehand, before putting the model into water, is actually making sure that the wind field is actually reproducing the characteristic of the wind side. We have been talking about the mid-ocean conditions are basically the key point for us to build from the scratch an effective test campaign. So, and to do so, of course, wave needs to be calibrated specifically and independently on the wind of the installation side, but also the quality of wind is a key point. And for doing that, we have developed this set of fans that actually allow us to basically have two different facilities in one, basically a high quality wind tunnel coupled with a high quality wave basin. And this is, I have to admit, is quite unique in the world, and it's in the Netherlands. So how a scale model look like? This is a very famous prototype of a semi-submersible concept delivered by the NRL, which is an open source, and an open source concept, and it allowed for almost 1 decade research institutes and also floating wind players to be playing actually with something that is an unexplored field. At least it was 10 years ago. And this is the concept that have been extensively tested at Marine, and we have been, let's say, building up our knowledge also to be serving more effectively the clients. And this is how it looks like. We are basically we want to put a lot of sensors without going into details, but sensors that can actually allow us to gather measures in operating conditions to be basically validating the numerical codes that we have mentioned that are being used by industry. So we place force sensors, displacement sensors, accelerometers all over, or let's say in a smart position, depending on what is the research question of the test campaign. You can see here quite a let's say a close look at how a scale model of a wind turbine looks like. And I have to admit that at Marine, fortunately, we have the engineering and manufacturing capability to actually produce quite high quality scale model for the wind turbines, because it's a key, especially if we also consider how much is the influence of the quality of the blade. I'm going to talk about briefly about that, and the dynamics of the control system, for example, on the overall dynamics of the platform. Typically, our clients are oil and gas platform manufacturer that are going into floating wind, and this of course this kind of campaigns are useful for them to actually fine-tune their design in order to be aware of what are the strengths, what are the motions, what are the forces on the mooring system, on the platform itself, and actually the loading coming from the, let's say, static and dynamic forces of the wind turbine are actually key in the overall design. But I mean, talking about this, it looks like that is very, very simple task, but this is not the case. If we look at these two graphs, one might say, okay, you have the curves of the, let's say, power and thrust coefficient that you want to be reproducing in a model scale, but they are actually quite different compared to the performance of the model scale. That is true, but that is true if we just scale down geometrically what is the wind turbine blade design. What you actually want to do is actually reproducing the same forces in a scale manner. So what you have to do is completely getting rid of the full scale design, redesign as you were a wind turbine manufacturer, specifically for the scale model performance of your wind turbine. That's the only way that you can, let's say, match the two curves. This sounds a little bit technical, but what, long story short, is actually you have to reproduce some kind of equivalent design of the rotor at scale model in order to be actually able to reproduce the full scale performance. And we can do that by thanks for our long-lasting experience in propellers. In the end, a wind turbine is not that different from a propellers, and we can make use of numerical codes that have been validated for decades. So these are the typical concepts that we have been testing so far. So SPAR, semi, and TLP. Which are actually coming from the, let's say, the oil and gas experience. But actually there are new philosophies also that I want to mention in floating wind turbine designs that are, for example, like this Tisdale concept, which basically it's the way around in terms of the approach. So here you have in the oil and gas approach, let's say oil and gas manufacturer, they are designing their platform and they are trying to make that as cheap as possible. In the other type of concept is considering from the very beginning of the design also the O&M and the transportation issues. So then considering those constraints as inputs, you come up with some design that can look like completely different compared to this type of concept. We have been testing since more than 1 decade, different concepts, and these are the typical testing campaign results of our previous experience. As you can see, these are different concepts for these different applications, and that they show also here different behave in almost comparable wave and wind loading condition. For example, just to mention one, the spar on the left is really acting like a pendulum. So it's like rotating back and forth quite a lot without moving transversely too much. Whereas on the other side, you can see the TLP, which is very stiffly connected. And so it can pitch really low compared to the other concept. This is like a typical offshore basin experiment. And you can see here, this is a little bit promotional, but I think it can give the idea of what testing floating wind turbines look like. So from the control room, we are able to control everything that is related to the control of the wind turbine itself and the generation of the wind and the wave. And as you can see here, the mechanism behind the performance of the rotor is quite important for the overall performance. So we are able to dedicate quite some precision details. It's almost done. Here, yeah, we have few concepts from a platform manufacturer that you might know. And like just to give you an idea, so the typical scale is 50. So this the fruit scaling, which is basically the way we are scaling down the forces and the motions, is more or less 1 to 7 for the wind velocity. So it means that we are actually able to reproduce up to more or less 6 meters per second in the basin, which means way beyond the cutoff of the wind turbine. This just briefly, I want to show you the last update of our research. This can be considered as the research of the research. So we are at Marine doing research in order to make the research of our client most effective. And here we are basically, long story short, substituting the actual wind generation by a set of wire that actually provide the force, the rotor force, as if the wind were blowing, but like basically helping out to loosen a little bit the scaling constraints that we have when we scale simultaneously wind and wave. This is actually the blue water concept, and I think the other speakers today are going to talk a little bit more about that. And yeah, just this very final movie, which is a promotional one, but at least gives you the idea of the two different setups with winches and with physical rotor that are actually available at Marine, depending on the goal of the on the. As offshore wind energy is growing and moving the ocean, Barge is the front line to serve floating offshore wind plants at key stages of the public life cycle, from concept to commercial and operation. Okay, that was a little bit promotional, but I think it was nice to see. And yeah, thanks. That was the end of my presentation. And I just three quick remarks. which I think is important, is that model tests, as it has been mentioned, are complementary, but also really important to be combined with the let's say with simulations. And at Marine, we have capabilities to help our clients to do both. And of course, we always tell our clients that investing in a scale model test campaign reduces quite a lot the risk, optimize the design, and in terms of cost, it's absolutely not comparable with what can happen with the wrong design at sea. And so, yeah, feel free to reach out if you have any questions. And that was it. I hope you.
Yeah, well, thank you very much. It was an absolutely interesting presentation, and you're really on the forefront of what's happening in the design area, of course, of these floaters. There are a few questions from the audience. There's a question from Hans, who also likes to thank you for the interesting presentation. And this question is related to, say, higher turbulence intensities. Can you also test them in some way? Or maybe are they less relevant? Can they be neglected?
Well, it depends on what does high turbulence intensity means.
Generating high frequency vibrations.
Yeah, that's a very good point. Basically, what we can do with our let's say wind setup is actually varying, making a slow varying, let's say control of the wind farms that actually can reproduce a turbulence scale that is typical, the one that is affecting the bigger motion of the wind turbine. For high frequencies, of course, it's might be a problem, especially with let's say high level, higher frequency, bending frequency, for example, of the tower, or higher natural frequencies of the blades. But that it depends on how actually you also build and design the model. If you have, for example, if you decide to build a rigid model, there's no, for example, need to look into the turbulence, but you will look at slow varying or even mean wind velocity. That will be more important. But if your concept and the research question are really related to high level and a high frequency, then the other type of concept, the one with wires, actually allow to also introduce let's say let's say in a controlled way the high frequency turbulence on the rotor of the wind turbine. But that is not going to be related to physical wind generation, but the effect on the overall design would be the same.
Yeah, a related question from Jan is about, say, the various movements. How does it influence, say, the fatigue loading of, for example, the gearbox? It's going to be different from a static wind turbine on a fixed foundation.
Yeah, indeed. Actually, what we haven't mentioned is we talk about integration, and integration. I'm a big supporter of the integrated design from a very earlier stage of the design itself. For example, if we think about the control, control is usually considered at the very end of the design value chain, but it's actually, especially for floating wind turbines, a key point that needs to be addressed at the very beginning. And I mean, if we look at the, for example, at the DNV guides and recommendation, of course, there's some, from an engineering perspective, there are parameters that need to be taken into account, and their effect on the drivetrain. Let's say reliability.
Yeah. Okay, I think we're so done with the questions. Thanks again, Ilmas, for your presentation, and
thanks for having me.
We're moving on also to the next presentation from Clemens van der Nat, who's manages strategic developments at Blue Water Energy Services. Clemens, the floor is yours.
Yeah, well, thank you, Bob. Well, I have to share my screen to get the presentation in place. And I think it works.
Yeah, it's
Well, yes, I will tell something about quite a different subject. Where we see that there are needs for this offshore market, this new offshore market, where there are the needs that actually can unlock then the potential of floating wind. It's quite a different subject. Actually, I was really surprised and also I think the previous speaker were already talking a lot about the floating wind market, but our view on that market is different. So I hope it gives also some discussion with the previous speakers. I like to of course to see the motions of the TLP in the basin, which shows that they are very minimum compared to the others. That is true. That is certainly true. You also showed the hybrid testing in the basin, which with the winches from our TLP. Actually, it was necessary because the wind loads, even if the turbine is not spinning and you are offshore the northern part of Scotland, the loads are so high that you cannot generate it with the wind machines. So you have to do that with the testing of the winches. So that was good to see that is necessary. Yeah, well, I will tell something else. So I will go to the next slide. Yeah, just a little bit about Blue Water, where we're coming from. Not everyone may know that we are in the business of oil and gas. So yes, our background is mooring of oil and gas facilities, big turret projects, but also in the Arctic and FPSOs. And since 5 years already, it's already a long time, we are working on floating wind. It's been actually a challenge. It's a lot of challenges in floating wind. Not only, let's say, the numerical side, which has been discussed already a bit, but also the market for floating wind is quite challenging because you need to demonstrate in order to have an entry ticket. And that is a very expensive ticket because these demonstration projects are really expensive. And that's also one of the reasons why I think there are very little demonstrators out there at the moment. And of course, all these people that have demonstrated want no one else anymore in the market. So they will tell everyone that demonstration has been done and that we have to move to the commercial side, which we of course agree, but I think there are also other reasons why they tell so. Yeah, we are in the business of FPSO, so we are in the oil and gas, so you can find us everywhere where oil is found. We see that we have a big presence in the North Sea, especially in the UK sector of the North Sea, so we are quite familiar with the ScotWind outcome. We have actually in all these concessions of ScotWind, we have 3 of our FPSOs. So we are also quite familiar with the environment, and I can tell you it's harsh. It's a very harsh environment. I think that even the demonstrators that are out there, which are mostly actually in very mild conditions, near the Canary Islands or in the Mediterranean, or even the ones that are in the North Sea in the UK sector are quite sheltered from the UK itself. So if you go to Scotland, in the northern part of Scotland, the wave conditions and the wind conditions are quite different from the ones that you can see in the normal test sites that we have at the moment. So yes, we are demonstrating. Yes, we are doing some things. There are small arrays, but I don't think that we are there. So there are a lot of challenges, also with respect to the technical part. Yes, and we also expect, of course, that there are projects in new areas for Blue Water. We will notice projects in the US. We have no presence at the moment because there's in these areas no oil and gas found yet. We never know what happens in the future, but at the moment it's not. So that means that also we have to expand our business to areas where we are normally not present. Well, the floating wind market, I think everyone that follows the news will see that there is a lot of news. Everyone is telling that it is a really big market. That is maybe true. At the moment, we only see some small demonstration units. It's compared to bottom fixed, nothing. Really, it's very, very small. We have high expectations, yes. And I think a lot of people are working on it, we as well. So we hope that these expectations will become reality soon, because everyone is very, not patient to go into this market. But yes, we have to make it. We have to make it through. So we also notice that this push is not only from the technical people, so from the developers, but also from governments. And I think that is the real push that we need to make this work. So what is our primary focus? Yeah, you told us that the European Union is far, let's say, a front runner. I disagree. At the moment, we notice that the Far East, and we don't even look too much to China. But at the moment, Korea is probably will have the first commercial projects, real commercial projects, far ahead of the ones from Scotland. Yes, so that means that at the moment the front runners are maybe European companies that are working in South Korea, in the Far East. We hope that all the ScotWind concessions will be taken for lease by the companies, especially the majors, because that also will give a push. But that has to be done. While in Korea, that is already done a few years ago. So there, South Korea is ahead, and I think for commercial projects, this is probably a better ground to be the first. Yeah, and there are many concepts. Yes, many funny concepts, many concepts. We have distinguished them between the semi-spar and the TLP and the barge, and everyone, I think, around the table knows these different concepts. Yeah, a lot of study work has been done in I think the last maybe 20 years on these concepts, and no one knows who's the best. Yeah, we focused actually on the TLP, and you would say, okay, why not on one of the others? When we did our evaluations for the decision which concept should we select, we very much focused on actually two aspects. One aspect is how do we want to approach this market as part of a supply chain, and the other one is how much steel, how much materials do we need to bring this concept forward, and what is the impact if the water depth increases or the environment becomes more harsh. And especially for the last reason, we selected the TLP, because if the water depth increases, of course it will have some impact on the platform, but quite limited. While for the others, the mooring systems really become heavy. So that is a major disadvantage for the others. And the harsh environment is also a big challenge. We from the TLP, we have relatively deep draft pontoons, so the impact of the waves is minimized. And you notice that not only in the model test basin, where you see less motions, but also, of course, at the end, it will reduce the size of the platform, and so the amount of steel that you need to, at the end, support the turbine in those environments. So that were for us reasons to move into the TLP business. It is also a more challenging, technical challenging platform. We always say it's like a guitar. It's a lot of vibration, a lot of high tension components, and they all need to be able to not only withstand the environmental loads, but also, of course, in the long term, the fatigue loads that are imposed on these structures. So that was where we started. I think now about maybe 4.5 years ago to start developing this TLP. And we know that our main competitor, which is SBM Offshore, selected more or less the same concept. A few little different items they have in their TLP, but at the end, it's more or less the same platform. And yeah, they also face a lot of challenges. I think also the technical part, because also they had quite some delays in their development, similar to what we faced. We also thought when we started this development that we would be in the water quite soon, but reality is that it takes more time than expected. What do all these structures have in common when you look at it? I think that in general you can state all these structures are huge. I mean, we show here some pictures of relatively small turbines that are on these structures. So like 5 or 6 megawatt and on the top one an 8 megawatt. And still they are massive. They are, and that's just a single unit. And don't forget, if we look at a farm, it's not a single unit. It will be 50 or 100 of these units. So that is the real challenge, and that means that it has impact on fabrication. We discussed a little bit about it, but also on transport, installation, and don't forget the maintenance. They are not maintenance free. I heard something about taking these structures back into a port. Well, I can tell you that there are majors that are really thinking that that is not a good idea. It will take a lot of time and a lot of downtime of the unit. And also, what I show you later is that the tow itself is also a challenge. So I think that the idea that it is cheaper to bring a unit into a port for maintenance and overhaul than doing the same activity offshore will not prove probably at the end to be true. It is of course mentioned a lot in floating wind as one of the key advantages, but no one has proven that it is true. So that again will also be a part of the exercise in the near future, where we'll notice whether that can be done or not. At least whether it can be done at a reasonable price levels. Or that we still see the same issues as with bottom fixed, where you have to do this maintenance offshore. So just some numbers. There are a lot of ambitions. Well, look at the ambitions of the EC and the UK. The UK is of course now not a part of the EC anymore, so they have to be different. Yeah, it's something like 17 gigawatt of installed floating wind power somewhere in 2030, which is a huge number. Don't forget, we have only at the moment, I think, around 12 gigawatt installed in the bottom fixed. So it's a huge, huge number. But that's the ambition. I mean, we all can have ambitions. I think you have noticed the Green Deal, where billions of dollars, euros in this case, billions of euros will be invested in renewable energy. So yeah, the governments want to have it. And the governments are we, the people. So the people want to have it, and we are going to pay for it. It will not be for free. That is for sure. But it also needs to be technically feasible. And if you look at 17 gigawatt of installed power, it means 1,500 floaters, each carrying the largest turbine ever, 12 megawatts, which is now in the port of Rotterdam. It's a huge turbine. And if you look at the amount of steel is about 7 million. Depends a bit on the concept. I'm thinking we are on the 4, of course, and the spar will be on the 7 side. But it's a huge number, 7 million tons of steel. Don't forget, if you look at Japan, they have about half of this number as the total fabricated steel of the whole shipbuilding and offshore building sector. So you need 2 times the capacity of Japan to make that happen. And in Europe, well, we are not so fond of steel fabrication only. We want to add value to shipbuilding steel by having installations and complex vessels. Well, this is just steel. This is a massive amount of just steel. There is nothing in there. It's just empty. It's steel. So you have to see that this is a big challenge for the world to make that happen, and to Europe as well. Well, these structures are not just simple rolled tubulars like we can see in the Netherlands and also in Poland and in the UK. They want to have factories that just have these tubulars, for example, for the monopile industry and for the so that they can make them here in a fully automatic manner. which is quite competitive. So we don't have to bring these tubulars from China. But this is for floating. It's fabricated steel. It's panels. It's a lot of stiffeners inside. A lot of welding. A lot of things need to be there. Steel, not complex ships, but just a lot of steel. And well, we are not. In Europe, at least, not outfit. We don't have an outfit for large amount of steel in a very cheap manner. We don't have the facilities at the moment. And if we want to do that, if we want to build that 5 to 7 million tons of steel between now and 2030, then we need to do something. Unless we want to have it built in China, all of it, or in Korea or in Japan. Which I think is also from a transportation cost, because these structures also need to be transported, maybe not the right way to go. So is there appetite in Europe to go again back to the 80s, where we had these big shipyards and were able to build, well, tankers, which are also just a lot of steel without a lot of equipment. That industry died just because of the cost per ton were too high, too many man hours. But maybe for this industry, it is still feasible again, because the repetition is so high compared to the shipbuilding. We have 50 or 100 of the same. Or if we make these units very friendly for fabrication, we can do a lot of automation with robotics or other smart ways. But that also needs outfitting, which I don't see happening at the moment, because that takes a lot of investment. And we also already know from, let's say, the others, so the tubular industry, that if there is a little bit of downside in this industry, some years where there's a little bit less employment, this industry is having a hard way. And you can notice the share price of SIF, it's going anywhere. And of course, also bankruptcy, because the one in Poland was actually earlier this year bankrupt. So, yeah, it's an investment, but maybe it needs to be combined with shipbuilding again.
Clemens, I'm also looking at the clock, and
yeah, I have 4 slides left.
Yeah, so I'm also thinking maybe about some more discussion, because these are very sobering words in a way, to temper the enthusiasm a bit. But there's also some optimism, because you also mentioned solutions. Are you also covering that?
Of course, I'll give you 4 more slides, and then you can start. It's not. I think we have to be realistic in this industry, because I think also there's our opportunities. It's not pessimistic. These are opportunities for the European industry to take, but it requires people that are willing to invest, and maybe with support of governments, these investments can be made. I think that is what we look for, and if that is not made, then of course someone else has to do it. The other big challenge that we see in floating wind is the marshalling. We talk about massive amounts of turbines and massive amounts of big structures that need to combine. If we do that in ports, then you need really big ports, because these structures are large and they take a lot of space. And if one of the supply chains, for example, the supply chain of the floater is hindered, then you have a piling up of the other supply chain of the turbine, because they are together in one port. That's also one of the reasons why we have a strong opinion that you should not marshal all the components to one location. And then the transport challenge. Everyone talks about tow for the floater. What we notice, and I think it's fair, that weather has a big impact on tow. And it also means that if you do towing, that you can have delays from weather, and there can be significant. We all know that the first array of the principal power floaters took quite a lot of time to install in the Atlantic last year. And so what we see is that especially if you go to areas where there's a lot of wind, and we want to go there because that's the resource, that there is also a lot of waves, and the weather downtime can be quite large. So you have to take that into account when you develop your technology, and notice that the weather downtime should not be hindering the development of your project. So what we notice that the supply chain solution that bottom fixed, and we are very much fond of bottom fixed in Holland, because we notice that this industry has matured, and the cost per megawatt installed is gone down a lot, and we still see that there is room to improve. But one of the key aspects in that development is in that whole optimization is the supply chain optimization, where you have the installation of your foundation and the installation of your turbines being split. Yeah, you have one season where you maybe install the foundations, and when the foundations are done and there is no delay possible for the turbines, then the turbines will be installed. And we are very much favor of that. So we think that the supply chain for floating should act in the same manner, where you also first install the floater, and then later, when all the floaters are installed, you will start installing the turbines. But then you need a floater to install the turbine, because you cannot go to a bottom fixed solution anymore. So we are happy that there are companies like Hirma investing in floating installation of turbines, and that is what we need. And we think that as soon as that market matures more, and there will be more floating installation of turbines, also the floater market will mature. Yeah. And then, of course, we need innovative solutions for that. And we already noticed that there is quite some innovative solutions in the Netherlands. We can see that Huisman is investing a lot in getting these turbines floating installed, but also Hirma is working on that with also slip joints for making this type of installations more easy and more competitive. Yeah. So yes, I think there is a lot of good news, but also we have to be realistic that we are at the start. We are not certainly not in a mature market yet.
Well, Clemens, thank you absolutely for a different viewpoint, I would say. And of course, we all are taken away by this enthusiasm, and of course by all the high targets. But clearly, we also need to solve some issues here. And I think this is, of course, where innovation comes into play as well. Innovative companies supported maybe by universities and research institutes like Marin, who could really help to make this, to find solutions for these challenges. And I'm looking at the clock. We have got another very interesting presentation waiting for us from Karel Rosen, who's the co-founder of Next Ocean. Taking a completely different angle again, looking at waves and the impact of that on floating structures. So what I'd like to do now is to park any time for discussion and questions, and first take the presentation from Karel, and then see if we have time to follow up on the issues that you raised, Clemens. Thanks very much.
Okay, no problem.
So, Karel, if you can take over the screen and start your presentation.
Yes, thank you, Bob, for the introduction. I just shared my screen. I hope it's well visible for everyone.
It is.
It is? Good. All right. Well, thank you for having me here tonight. I have nearly not as much expertise as the previous speakers on this topic. Nevertheless, I have a lot of slides for you, so I'll just rush through them, see if I can make up a little bit for the lost time, and that we have them still some room for questions in the end. So, yeah, Next Ocean, I will shortly introduce the kind of technology that we developed and that we sell to the offshore industry. So the challenge that we tackle with our technology is the unpredictable extreme waves. So with lots of different offshore operations, somehow you always have to deal with these waves and the wave-induced ship motions. That can lead to certain accidents, even injuries, or in the worst cases, loss of life. And the only way that we currently have to prevent or to somehow fight this unpredictability of these extreme waves is to apply huge safety margins, which of course result in a huge opportunity cost for the offshore industry as a whole. Now we have the solution for this problem. That is that we predict the future. So we use the vessel radar to actually scan the waves around the ship. And then we use our software to predict the incoming waves and the resulting motions from these waves. Therewith, we both reduce the risks of these operations because we take the guesswork out of the equation. And in the same way, at the same time, we can increase the uptime because we can still indicate those windows of opportunity where you can perform your most critical part of the operation, even in the conditions near or slightly over your conventional operational limits. So this is how the product looks like. So we really allow the crew to safely time the most critical operations. And that's what you see here also in the interface. And just to keep a long story short, you can imagine it as a traffic light with a timer. And the traffic light is green if everything is okay. And it will switch to amber when it foresees a limit crossing motion to be upcoming in the near future. It will switch to red when it is happening and back to green when the dangerous or more unsafe situation has passed. Also in the lower corner here, it's maybe interesting to mention, you see a directional wave spectrum that is a in situ measurement of the wave condition, and it can help to optimize your heading in the current sea state. All right, I will just round up this introduction about our technology before I move on to the floating wind and offshore wind in general and our role in that sector. I will round this introduction up with a concrete example. So here on the left, you see again our interface, and in the top bar here we see a now. This white line is representing now at this moment, so to say, and all to the left of this is history. And we can see that if we would judge the condition by this recent history, we would say like, well, we have like one tiny motion crossing or motion limit crossing event, but in general, it looks fairly calm. We could decide to start a critical operation at this very moment. Well, the wave predictor is capable of looking also ahead of time. And then suddenly we see that actually this is upcoming in 2 minutes from now. So this is just literal screenshots. I just made photos of a live project somewhere out at the North Sea. And if we look now to how the interface looks like a couple of minutes later, so here this event has passed. And if we then see the monitoring graphs where we monitor the actual recorded motions, we also see that these predicted waves, these predicted limit crossing motion events indeed also occur. It was a very severe window. All right, so over to the floating wind and our role in the floating wind. So when I was preparing this presentation yesterday, I directly had to think of this graph. It's like a little representation of how the developments went for the oil and gas industry. And I know this from a lot of different lectures that I had back in university. And it also started in the little bit shallower water with bottom-founded structures, and over the years into the more recent developments, it went further offshore to deeper waters, and somehow the end stage of this development was subsea, to bring just everything to below the water level. Well, I don't expect something similar to happen with the floating wind, of course. We don't have too much to do subsea, but in the floating wind, we see the same kind of development. And here the end stage will be probably something more in this kind of fancy concepts, which are under development currently, but we are still far away from that, obviously. Well, why is it interesting to think about this floating wind? As far as I could find some facts on this, is that 80% of the somehow interesting areas in the near coastline areas, where there's also a lot of cities situated, roughly 80% of this area is over 60 meters deep, which means that the bottom-founded structures get less or cost-effective or even economically unfeasible. Well, so our technology helps actually over the whole range of offshore wind and offshore floating wind concepts. And so, because in general, by predicting the waves and by predicting motions, you can benefit from the technology that we developed both in the bottom-founded wind turbines as well as in the floating wind turbines. Nevertheless, recently we also got involved in a project that was really more specifically focusing on floating wind. And in this case, it is about a semi-submersible type of floating wind turbine. And that is the design by Ideal. It already appeared in some of the previous presentations. I think Clemens showed it. And their concept is a semi-submersible with a dampening pool in there. So this dampening pool is designed as such that the sloshing that happens in there somehow counteracts the wave-induced motions of this platform. And the goal, of course, is to somehow keep these turbines as stable as possible. Well, here's another little bit more photo in detail. So this is the floater here. You can also see how it looks like underwater, for those of you who are interested in how this would look like. So we ended up in a consortium that together applied for EU funding in the Horizon 2020 project, and it's called Flowtech. So we are now one of this list of companies, great companies to collaborate with, and we as the Next Ocean also play a role, a significant role in this project. So what is the goal of this Flowtech project? Well, in the end, the goal is to overall reduce uncertainties in the design process. And in the end, of course, to increase the cost competitiveness of floating offshore wind. The main way how this is foreseen to be done is to optimize certain design software. It's called QBlade, and this QBlade software can help to optimize the design of your offshore floating wind farm. Now that is for the design phase, but simultaneously they tend to use this software also during operation for both AWM and AWC. Now what does this stand for? The AWM stands for Active Wave Management. Now, this is a famous picture, probably all of you that are attending today will know it. It clearly shows on a misty day what the effect is of, or how actually the wake of certain turbines, even though they are spaced far apart, still affects the other turbines. By adjusting the nacelle heading, you can slightly improve this, or actually reduce these effects on the other turbines of these wakes, and therewith increase the efficiency of the whole wind farm. But that's not where we come in. We come in on the AWC, which is an acronym for the Active Wave-Based Control. So floating turbines, as you can imagine, they can move in the waves, as opposed to bottom-founded structures that are just stiff connected to the bottom. The floating turbines can move. I'm familiar with these kind of plots where we can see that a ship can move in different degrees of freedom, the same way the floating offshore turbine can do so. And actually this is a problem because the movement of these turbines increases the fatigue loads and also reduces the overall efficiency of the turbine. Now, one way to counteract these motions is by active pitch blade control. So by changing the pitch, you can change the moment that is induced by the wind force on the turbine itself, and therewith you can control the position. This is already done. This is already active in some floating offshore wind turbines, but it focuses mostly on the motions induced by the wind forces. On the other hand, of course, also the waves have a similar effect. Also, the waves will make these turbines move. And that is where we come in as Next Ocean with our wave predictor. So we are contracted within this consortium to deliver one of our products for this Ideal turbine. And the idea is, or at least what we try to achieve here, is to see indeed if it's possible by wave feed forward to reduce these fatigue loads, to also use the active pitch control of the blades of the turbine to counteract the wave-induced motions, and in the same time also increase the efficiency of the turbine. Well, this project planning, the project starts January 2020. We will be involved in a like full-scale test for the full 3 years that the project takes, so from 2020 to 2023. But unfortunately, it will still take some more demonstration project, at least that is their expectation, before this technology will be commercially applied. Luckily for us, as I already mentioned earlier, our technology is also applicable on the bottom-founded type of offshore wind turbines. Also, these need to be installed and maintained in harsh offshore weather conditions. So to give some examples of these kind of operations where there's like a critical short moment where you can benefit from the wave predictions and ship motion predictions, you can think of walk-to-work operations in the operation and maintenance phase, but also think about the installation phase where TP installations take place. There needs to be trenchers launched and recovered for cable trenching, and also the feeder barge concept, which is upcoming. And for those who are not familiar with this, the feeder barge concept works as follows. There is like a jackup vessel that performs the actual installation of the turbine components, and because it's jacked out of the water, it is not influenced by the wave motions. But here, of course, the critical operation becomes the loading, or like the picking up the components that are fed to this jackup vessel by the feeder barges, because these feeder barges are actually subjected to the waves. Now, last but not least, also even pre-installation, you can think about survey works where there's also ROV launch and recovery operations taking place in harsh weather conditions. We have done quite some projects so far, and we also made some videos about these. I will not show all of them, you can find them on YouTube, but there's one in particular, here the latest one, which is really about the offshore wind. And it's not floating though, but still I would like to show you this video just to get an idea of how this technology works. So this project took place in December 2019. And we have been active with our technology on the Acta Auriga from Acta Marine. Here you see the interface, but then live. So you see actually the predictions scrolling from future to the history. And in the next shots, you will see some predicted severe motions also actually taking place when they hit this now line. And as soon as the graph shows that the severe motions have passed, the ship also stops moving almost.
Well, Karel, that was absolutely fascinating to see how this technology can also add to safety and increasing workability. And that you found an application actually in floating offshore wind. That's also very interesting. I'm looking at the clock. It's 6 o'clock. Sorry, 7 o'clock now. This is basically the time we had planned for this event. I realized that there are still open questions, and I think particularly, of course, the discussion that was triggered or could be triggered by the remarks of claimants that we'll have to follow up in that in another way. At least it set me thinking about what we can actually do with his remarks. But also I think for the other presentation that we've seen, there may be questions still left open that we can't cover today. I'm looking at Ashley and Tessa also to distribute the presentations and check that, of course, with the presenters what we can actually distribute. So there will also be contact details then of the presenters, that if you want to follow up with them on these various subjects, that you can actually do that. It's Karel, if you can stop sharing your screen,
Sure.
then basically, as I said, we've come to the end. I'd like to show you some last remarks before we close. So you now should be looking at my screen again. I would like to thank all the presenters today. It's difficult to get a real applause, but okay, this virtually have to do this. I think there were also questions raised about support for, say, financing support for floating offshore wind projects, in particularly for the Netherlands. I will pick up on that myself later on. But there are, of course, say, instruments available, in particularly from the European side. But also, if it comes to, say, applications in the Dutch North Sea, there could also be opportunities here as well. But more important, if you have ideas of your own and you want to, say, develop products or do research, find partners for research, then you can contact Buccaneer Delft, Maritime Delta, or TKI Wind op Zee. We're all ready to help you with either with questions or with project support in any way. So with that, I would like to close this event and thank you all for your attention and staying with us even at 7:05. Thank you very much.
Yeah, thank you too. Merry Christmas.
Thank you.
Of course, I wish you all very happy holidays.
Happy holidays. Take care.
Thank you, Bob.